Alrighty folks, this is our last installment for Unit 9, Chapter 8, last section, 8.5. We're scaling three-dimensional objects again, but now we're going to talk about their surface areas and their volumes. Okay, so we're going to understand the effects of scaling on surface area and volume, and then we're going to write scale factor formula for those, and then we'll do a couple of questions where we apply these ideas of squared and cubed scale factors to some contextual problems. Okay, so the effects of scaling on surface area and volume. So, giving you a couple of diagrams here. The first one is just a cube, okay, and it's a 1 centimeter cube. So I'm going to apply a scale factor of k equals 2. So all the dimensions, or all the edges of the cube, are going to get doubled, okay? And what you end up with is a bigger cube that instead of being 1 centimeter on each side now is 2 centimeters on each side, okay? So let's see what happens to the surface area, sort of a before and after snapshot, and to the volume in a before and after snapshot. So for the surface area, all of our surfaces were 1 by 1 to start with. So they all had an area of 1, and there were 6 of them. So that gave us 6 square centimeters for our original surface area. Okay. For the volume, length by width by height gives us volume, and since they're all 1, our original volume is 1. Whoops. I was going to write cubic meter, but it's not. It's 1 cubic centimeter. Okay, scale it up by 2 and see what happens. Surface area. I've got 1, 2, 3, 4 1 square meter bits to each face. So each face is 4 square centimeters. All right, and there's 6 of them, so that makes 24 square centimeters for the surface area after it's been scaled up by a factor of 2. Let's look at the volume. So length by width by height here is going to be 2 by 2 by 2, which is 8 centimeters cubed. So notice with a scale factor of k equals 2, our surface area got multiplied by 4. 6 times 4 gave us 24. And our volume got multiplied 1 times 8 to give us our new volume. Well, those numbers are both related to the k equals 2. This one is 2 squared, and this one is 2 cubed. Okay, so the effects on volume and surface area, if we compare those to the scale factor, the surface area gets multiplied by the square of the scale factor, and the volume gets multiplied by the cube of the scale factor. And we can rearrange those formulas to help us find the scale factor in terms of a ratio of areas or a ratio of volumes, just like we did before. All right, let's do some questions. A standard basketball has a radius of about 5 inches. As a promotion for an upcoming game, an NBA team wants to place a giant inflatable model of a ball outside their stadium. Weird. The giant basketball is to be created with a scale factor of 60 to 1. How much vinyl material is required to create the large ball? Okay, so first of all, what's the surface area of a regular ball? So the actual surface area. Well, surface area of a sphere is 4 pi r squared. So in this case, we've got 4 pi times 5 squared, which is 4 times 25, 100 pi, which is going to be about 3.14 times 100. So it's about 314 square inches. Okay. Now, what is going to be, how much vinyl material is required? So what surface area do we have on the large ball? I have to multiply my 314 square inches, which is my area of my image, of my actual. I have to multiply by that square of my scale factor, which is 60. Okay, so what I have here is 314 multiplied by 60 squared. And that's a huge number, but remember we're working in square inches here. So that's going to be 1,130,400 square inches. Okay, that's a lot of material. Okie doke. A model of a new reservoir, so a cube scale factor here, is holding 1 liter of water. So what's the scale factor that's required? if the actual reservoir must hold 1,000,000 liters of water. Wow, okay. So remember what we said, scale factor cubed is the ratio of the volume of the image, or the new thing, the model, divided by the volume of the actual. So what scale factor was used to make that model? Well, we know that the cube of that scale factor is going to be the 1 liter of water that we had for the image divided by the 1,000,000 liters that we have for the actual reservoir. So I'm going to get my value for K here by simply taking the cube root, remember our radicals unit now, 1 over 1,000,000. So the cube root of 1 over 1,000,000 is 1 over 100. Okay, so right here, 1 over 100 is the scale factor required to make that model that we're using. Quick summary. So whenever we create a scale model of an object, the ratio of the surface areas results in the square of the scale factor. So the surface area of the scale diagram, we get that by multiplying the area of the actual object by the square of the scale factor. And if we want to go in the other direction to get the area of the actual object, we divide the area of the scale model by the square of the scale factor. And when creating a scale model of an object, the ratio of the volumes gives us a cubed scale factor. So the volume of a scale model can be found by multiplying the volume of the actual by the cube of the scale factor, and vice versa, the volume of the actual object is found by dividing the volume of the model by the cube of the scale factor. Lots of stuff there. Good practice questions coming up. End of the unit. Hard to believe. Thanks.